Hello, this is the final from fall 2018, and we're just going to jump into it. If I remember correctly, this is one of the more difficult ones, so we will see how it goes. Okay, first question though, it's not difficult. This is about as easy as it can possibly get. Which of these planes are orthogonal to each other? Well, we know that two planes are orthogonal if their dot products are 0. And let's go from the bottom up, actually, and you'll see why soon. So taking the dot product of 8, 5, 0 with 0, 3, 6, what are we going to get? Well, we're going to get 15, which is not 0. And moving up 1, if we take this dot product, we are going to get 45. If we take this dot product here, we are going, well, we can express this as 1, comma, -3, comma, -5, dotted with 8, -6, 2. And this will be 8 minus 16 minus 10. And I don't care enough to do the addition because that's definitely not 0. So we've ruled out these guys. And looking right here, if we dot 5, 8, 0 with 0, 1, 6, that is also most definitely not 0. But if we take a look at answer choice A, we have 1, 10, -1 dotted with -9, -1, -19, which will give us 9 plus 10 minus 9, -9 minus 10 plus 19, which is indeed 0. Which of the following equations produces a surface that is not shown here? So if you generally have issues identifying these surfaces, there are some great visualizations of what they all look like out there. You can just run a Google search. Because really the only prerequisite that you need for this is to be able to match the patterns of, okay, what is the general equation for, say, an ellipsoid look like? And if you can match those up, you will be good, because we have a hyperboloid of two sheets, we have an elliptic paraboloid, a hyperbolic paraboloid, and an ellipsoid. So let's find these four equations in our answer choices, and the one that's left will be the odd one out. Well, we see that we can rearrange A into the form, let's see, x squared minus y squared plus z squared equals -1, and these two are our classic forms for a hyperboloid of two sheets. So A is out, and we see that that is there. Then B, right here, we see that we can generalize this equation as some x squared plus y squared plus z squared equals 1, which is our classic equation for an ellipsoid. So that's out. For C, we see that this is the general equation for a hyperbolic paraboloid that we see here. And finally, our elliptic paraboloid is right here. And so really, there's not much that you can do besides just knowing these things. If this is something that you feel like you're a little rusty on, go take a look at the whole video doing all of the quadratic surfaces questions, and I go into a little bit more depth about what these general equations are actually doing. But yeah, these questions are okay. Okay, find A so that the point 3, a, 1 is on the tangent plane to this guy at 0, 1, 4. So we know that our tangent plane is going to be expressed as z minus z naught is equal to zx x minus x naught plus zy y minus y naught, where zx and zy are our partial derivatives evaluated at 0, 1, 4, and our naughts are this is x naught, y naught, and z naught up there. So let's find all these values and plug everything in. So zx is going to be y e to the xy minus 8xy. Zy is going to be x e to the xy minus 4x squared plus 6y. And we can evaluate these guys at 0, 1, 0, 1, because our 4 is, our only z is out there. So at 0, 1, anything with an x in it, so this term, this term, and this term are all going to be 0. And so all we're dependent on, and also our e to the xy, but all of these are going to work out to 1. So this is going to simplify down to 1, and this is going to simplify down to 6. So now we actually have everything to set it up with, that we need to set it up. So we are going to get z minus z naught, which is 4, is 1, which is zx, x minus 0, which is x naught, plus zy, which is 1. Sorry, when I said 1, I meant 6, y minus y naught, which is 1. And so now all we're doing is plugging in 3a and 1 and solving. So z is 1, so 1 minus 4 is 3 minus 0 plus 6a minus 6. And we can simplify this down a little bit. This will be the same thing as negative 3 equals 3 minus 6 plus 6a. And this will be negative 3 over here, and 0 is equal to 6a, so a is 0. Okay, let's find the directional derivative of f of x comma y, where that is root 4x squared plus 3y at 3, 2 in this direction. So we know that our directional derivative is going to be the gradient vector, so fx comma fy dotted with the unit vector of the direction that we are pointing in. So that's going to be I hat, j hat in this case. So we can solve for all of these and get our answer pretty quickly. Fx is going to be 4x over root 4x squared plus 3x, plus 3y. Fy is going to be 3 over 2 root 4x squared plus 3y. And we can plug in the point that we're currently sitting at in order to figure out what our fx and fy is. This is going to be 8 over root 16 plus 9, or root 25, so just 5. And this is going to be 3 over 2 root 25, so 3 over 10. And just for ease of the calculations later, we'll turn this into 16 over 10. So now we have our fx, fy vector, which is 16 over 10, comma 3 over 10, and this is, as we know, the direction of greatest ascent of our function. But we want our directional derivative, so we have to take a dot product with 1 comma negative 2, except we have to find the unit vector of this, which is just going to be dividing it by its magnitude, which is going to be 2 squared plus 1 squared, which is just going to be root 5. And so I like moving these in here, so we have a root 5 and a root 5 under there. And now our dot product will just be our answer. So 16 over 10 root 5 minus 6 over 10 root 5 is going to be 10 over 10 root 5, or just 1 over root 5. For this level surface, we are finding 2 times the partial derivative of z with respect to x plus the partial derivative of y with respect to z at this value. So we know, this is some implicit partial differentiation, we know that partial z partial x is going to be the same thing as the negative dx over dz. And in the same way, we know that partial z partial y is going to be minus dy over dz. And so all we have to do is take 2 times this thing and add that thing, and then we will be good. So let's set this up. Let's find dx, dy, and dz, and then smack everything together at the end. So ddx is just going to be z squared. dy is going to be 6yz, and ddx, sorry, this is an x, this should be a z. ddz is going to be 3y squared plus 2xz. And now we can evaluate these at 1, negative 1, 2, and we'll get some easier numbers to work with. Z squared is going to be 4. 6yz is going to be negative 12. Yep. And 3y squared is going to be 3 plus 2xz is going to be 4, so this will be 7. And so now all we have to do is do what we set up here and set up 2 times negative ddx, so negative 4 over ddz, which is 7. And we are adding to that negative ddy over ddz, which is going to be 12 over 7. So we have negative 8 over 7 plus 12 over 7, which is going to give us 4 over 7. Okay, here we have a Lagrange multiplier question. We are given the function that we're trying to find the minimum of, and then we're given some constraint here. And we know that we can, they're already calling this f of x, but we know that we can call this constraint over here g of xy. This is f of xy. And we know that fx is equal to gx lambda, whereas fy is equal to gy lambda, where lambda is just some constant that makes these two gradients parallel, at least so I'm told. So we can solve this system of equations, and by plugging the relation that we get back into our g of x up here, we will be able to get an answer out of it. So let's set these things up. Fx is going to be 2. Fy is going to be 3. Gx is going to be 4x plus 5y. And gy is going to be 5x plus 8y. So setting up these equations, we have that 2 is equal to 4x plus 5y all multiplied by lambda, where 3 is equal to 5x plus 8y all multiplied by lambda. So we can use lambda to our advantage in here by setting 2 over 4x plus 5y equal to 3 over 5x plus 8y, and setting both of these equal to lambda. And now we can multiply everything back up to the top and solve. So 12x plus 15y is going to be equal to 10x plus 16y. This will give us 2x equals y, which is exactly the kind of nice clean relation that we want to get out of this thing. And we know that from here we can plug this back into our g of xy. I need a little bit more space, so I'm going to get rid of that over there. Okay, so if 2x equals y, for every y that we see up here, we'll replace it with a 2x. So we have 2x squared plus 5x times 2x plus 4 times 2x quantity squared, and that's equal to 28. Well, this is going to be 2x squared plus 10x squared plus 16x squared is 28. And this adds up to 28x squared is equal to 28. So x is plus or minus 1. And we know that y is 2x, so y is plus or minus 2. And then if we look up here at our function, we see that in order to minimize it, we'd like to have a negative y and a negative x. So negative 2 minus, I'll be a little more clear. 2 times negative 1 plus 3 times negative 2 plus 2, well, that's going to be negative 8 plus 2, or negative 6. And we're done. Question 7. Let f of x and y equal this guy, and we are asked to figure out by the second derivative test what kind of relative extrema this function has. So we know that in order to, like, our relative extrema will exist when fx, it's really not a plus, but fx and fy equals 0. And we know that given these relative extrema, we'll need to solve the little matrix here that's made out of fxx, fxy, fyx, and fyy. And we know that if the discriminant is greater than 0, we have two options. Either fxx is greater than 0, and that means that that the point that we're checking is a minimum, or fxx is less than 0, which means that that point is a maximum. Additionally, if the discriminant is less than 0, we have a saddle point, and if the discriminant is equal to 0, we don't know anything. So I'm going to keep these rules around. Hopefully we'll have enough space for them, and let's see if we can figure these things out. So okay, I meant to write an x, but that looks like a y, so I guess we're taking fy first. Well, fy is just going to be 2y e to the x, whereas fx is going to be, let's see, we can expand this thing out to f of xy is equal to x squared e to the x plus y squared e to the x. And so fx is going to be y squared e to the x plus 2x e to the x plus x squared e to the x. And so this is going to get even more complicated once we have to take an fxx, but we're not there yet, so it's all good. Okay, so we need to figure out the points for which both of these guys are 0. Well, it looks like 0, 0 will do the trick. Everything's multiplied by either a y or an x. So 0, 0 works. And if we look here, every answer choice only mentions 2 points. So really, we're only looking for one more point. And it's going to be a point where x is equal to 0. It seems pretty fair to say. We really like to avoid having e's, like e's that don't go away involved. So let's say our other point, it should probably start with x is equal to 0. At least that's a good thing to go with. And if x is equal to 0, well, okay, we do run into a problem because up here y would have to be equal to 0, and that's already a point. So if e is not equal to 0, let's see. If y is equal to 0, x can be equal to negative 2. Let's see how that works. If y is 0, this guy's 0. This piece here is 0. This guy will be negative 4 e to the negative 2, and this guy will be 4 e to the negative 2. So that works out. So it looks like these should be our 2 points. So now let's find our second order partial, what are they called? Partial derivatives, and we can solve. So fxx is going to be, I'll head down here, fxx is going to be y e to the, oh, I deleted a squared, y e to the x plus 2e to the x plus 2x e to the x plus 2x e to the x plus x squared e to the x. Isn't that just great? And then we know that f y is going to be 2e to the x, and f yx, which will be the same thing as fxx, sorry, fyx, which will be the same thing as fxy, is going to be 2y e to the x. So let's figure out what our values are for each one of these points, and let's set up our matrix. So for 0, 0, fxx, well, everything with a y out front or an x out front is going to be 0. So the only thing that's going to be non-zero is this 2e to the x, which is just going to be 2. So our matrix is starting off with 2. And then if we move down here, that's going to be 0. Come on, can't erase. There we go. That's going to be 0. So we have zeros in those two places. And then fyy, we're also going to have 2. So our discriminant is positive, and our fxx is greater than 0, so we have a minimum. So let's see, we have a minimum here and a minimum here. So that's something to keep in mind. Now let's look at -2, 0. So looking through everything, fxx, kind of dreading going through this. This will be, well, we can pull an e to the x out of everything, and we will get y plus 2 plus 4x plus x squared. And if we plug -2 into this and 0, we are going to get x squared. We are going to get e to the -2 times 0 plus 2 plus -8 plus 4. There we go. So this will all work out to -2. So we have negative, this problem takes a good bit of work, -2 e to the -2 as our fxx, then our fxy and yx will both still be 0, and our fyy will be 2e to the -2. And thank God our discriminant is negative, so we have a saddle point, and so our answer choice should be E. Okay. Thank God. I kind of despise this question. This is it's kind of an upsetting way to test this kind of thing, but I mean, someone thought that this was a good idea to have people do, so we got to do it now. Hope they don't do that on our exam. Okay, let D be the region in the first quadrant between the circle of radius 1 and the circle of radius 2. We can graph that out. Circle of radius 1, circle of radius 2. We want this region here. Oh, sorry. And they said first quadrant. So disregard all of that in there. We're just looking at the first quadrant. So that's telling us that we should be able to put this into polar coordinates relatively easily. So we can set up our double integral. We know that our region is going to run dr d theta from 1 to 2, because we want nothing in here, but we do want everything from radius 1 to 2. And then on theta from 0 to pi over 2. And then as our integrand goes, this denominator here will be r squared to the 3 halves, which is just going to work out to r cubed. So we have something over r cubed, and there's always an r sitting in here, so we'll put that there. And then x squared y, that's just going to be r cubed cosine squared theta sine theta. So simplifying everything down, we can get rid of, oh no, whoops. We can get rid of a lot of things, and we are left with r cosine squared theta sine theta, which is good because we can do some u substitution later on down the line. So let's disregard this for a second and just focus on the integral from 1 to 2 of r dr. This is going to be r squared over 2 evaluated on 1 to 2. This will be 2. This will be 1/2. So we're left with 3/2, times the integral from 0 to pi over 2 of cosine squared theta sine theta d theta. Let's set u to be cosine of theta and du to sine, negative sine theta d theta. So we can rewrite this integral as the integral from 1 to 0, well, 3 over 2 times the integral from 1 to 0 of negative u squared du. And we know that we can flip this sign and flip the bounds of our integration. So the integral from 0 to 1 of u squared du. And this is going to be u cubed over 3 on 0 to 1. That'll be 1/3 multiplied by our 3 over 2. We will get 1/2. Okay, which of the following integrals represents the volume of the solid in the first octant bounded on the side by the cylinder along the z-axis of radius 2 and on top by this surface, which is not necessarily something that we, oh, yeah, actually it is. This is z equals 4 minus x squared minus y squared, which is just going to be the paraboloid opening downwards from z equals 4. So we see, okay, so we have this guy, and we also have the cylinder of radius 2 in here, which is also running up and down. So let's figure out what is going on here. They want the volume of the solid in the first octant bounded by both of these guys. Well, if we take a look, this guy, our cylinder here, isn't actually bounding z at all. It's unbound on z. And so our z bounds are going to run from 0, which is just the bottom of our, the bounds on our first octant, to this expression that we've already seen here. We see it's going to be an opening, a downwards opening kind of paraboloid, which will be expressed by z equals 4 minus x squared minus y squared, which we see here and here and here. So these two are automatically out. And then we know that for our other two integrals, we just need the xy plane projection of this shape. So let's put our first quadrant on here. And we know that the projection of this guy can just be found by disregarding the x. So this is going to be x squared plus y squared equals 4. And that's just our circle of radius 2. And we can express that as y running from 0 to y equals root 4 minus x squared, and then x running from 0 to x equals 2. So let's see if any of these answer choices do that. And yeah, this one does. And there's our answer. Let's convert this integral into cylindrical coordinates and evaluate it. So taking a look at our first integral and our integrand, this is going to become the integral from 0 to 4 minus r squared of 15r r dz. And then for the rest of it, we can just graph this thing out. So we're looking at the upper semicircle given by y equals 4, root 4 minus x squared. And then x is running from -2 to 2. So we can add an r dr, and r seems to be running between 0 and 2, and a d theta, where theta runs from 0 to pi. And we see we're not bounded on theta at all, so we can multiply by theta out here. And we can bring this r in here. And we're ready to go. Since we're not bounded on z at all we have to do is multiply this thing in, and we're left with the integral from 0 to 2 multiplied by pi of 60 r squared minus 15 r to the 4th dr. And this is going to become pi times the quantity 20 r cubed minus 3 r to the 5th on 0 to 2. This is going to be 8 times 20 minus 3 times 32, all multiplied by pi. And now let's figure out what that is. Well, 8 times 20 is going to be 160, and we are subtracting 96 from it. And we will get 64 pi as a result. Okay, let's compute the triple integral over the region E of z dv, where E is bounded by the unit sphere and the coordinate planes in the first octant. This is a classic spherical integration question. They've asked this exact question down to the individual words twice. So this is a very common thing to have to know how to do. We know that z in spherical coordinates is rho cosine of phi. That'll help us out. And since we're only bounded by the coordinate planes, this will be an easy integral to set up. Theta is going to run from 0 to pi over 2. Phi is going to run from 0 to pi over 2. And rho is going to run from 0 to 1. Our integrand is rho cubed sine phi cosine phi d rho d phi d theta. And if it's confusing why we're bounded by pi over 2 in both cases, well, if we look at kind of the graph of what we have to do here, if this is a z, x, and y axes, phi can only go down to the y-axis, to the xy plane, and theta can only go around 90 degrees. So in both cases, they both have to be bounded by the equivalent of 90 degrees, which is pi over 2. Okay, so we're ready to evaluate. Let's disregard this sine phi cosine phi for a second and just take the integral from 0 to 1 of rho cubed d rho, which is just going to be rho to the 4th over 4 on 0 to 1, which is just 1/4. So now we have the integral. Oh yeah, and while we're at it, we might as well get rid of this d theta and just put a pi over 2 there, because there are no thetas in our integrand. So we have the integral times pi over 2 from 0 to pi over 2 of 1/4 sine phi cosine phi d phi. And we can use a nice little identity that says that sine phi cosine phi is 1/2 sine 2 phi. And so let's do that. We have pi over 2 times the integral from 0 to pi over 2 of 1/8 sine 2 phi d phi. We can integrate this. I guess I'll head over here. This will be pi over 2 times the quantity -1/16 cosine 2 phi on 0 to pi over 2. This will give us 1/16. This will give us negative 1/16. So overall, we have 1/8 times pi over 2, or pi over 16. A particle is traveling along the path y equals x, so we might as well just go put that in there. Y equals x, y equals x, y equals x, y equals x, and y equals x from 0, 0 to 1, 1. Which of the following force vector fields is for which of the following force vector fields is the work done equal to 0? Well, if you're in Physics 172 or you've taken it in the past, we know that the work done on a particle, you can kind of think it as the force that the vector field is giving to either help the particle along the way or keep it from going along its path. And the only angle that you can push something at where you will neither help it nor hurt its path forward is a 90-degree angle. So we are looking for a case where the particle is neither being helped nor hindered along its path, and where the force vector field is always at a 90-degree angle to that particle. So in the first case, nope, no 90-degree angle, no 90-degree angle. Definitely not, and that's exactly what we're looking for in question D. Now, they could throw something at us if they were feeling clever. We could have, a particle moving through an equally alternating set of arrows, force vector field, and these could be at any angle as long as the next one canceled out the one before it. There would also be no network done. That would just be a little more hairy for them to ask about. Okay, we are given that this force field F is the gradient of some potential function F. And we are looking for, well, they say gradient of F is just F. Gradient of the potential function F is just F. So they're looking for the line integral F dot dr of this curve. So this is a perfect case for the fundamental theorem of line integrals. It says that F dot dr, if, sorry, I don't want if F is the gradient of some potential function F, then this is going to be equal to that potential function F evaluated on the start point of your path and the end point of your path. And we know that this is because conservative vector fields, which are vector fields that are the potential, that have potential functions, are path independent. So it doesn't matter what path I take between A and B, we could circle A a bunch and head over there. It doesn't matter what we do, we could take a straight line. It will all give us the same F dot dr, which is the same thing as the amount of work done by the field on the particle. So in order to figure this out, we have to take antiderivatives of each component of our force vector field in order to figure out what our potential function F is. So these partial antiderivatives are going to work out to 3x plus x squared y, comma, x squared y minus y cubed. And we see that we have overlap here. We're only going to count this overlap once, so F is going to be 3x plus x squared y minus y cubed. And you can see, and you can do it on your own if you want, if we take the gradient of this guy, we will see that we in fact get our answer. Our gradient, the x component of our gradient is going to be 3 plus 2xy, and our y component is going to be x squared minus 3y squared. So this satisfies things. So that is our potential function. Now we just have to figure out what the x and y coordinates are for the path that we're taking. Well, we see that r of t is given here, and we're given the bounds on t, so we can just figure it out. R of 0 is going to be 0, 1, and r of pi is going to be 0, comma, e to the pi times negative 1, or just negative e to the pi. So looking over here, we're going to evaluate it on our endpoint, so 0, comma, negative e to the pi, and we're going to subtract 0, comma, 1. And then evaluating, we see that anything with a x in it, so these two components, in both cases, they're just going to work out to 0. And so all we really care about is this y. So negative e to the pi cubed is going to give us e to the 3 pi. And then we see that down here, this is going to give us negative 1 cubed, or just negative 1. And so our answer is A, e to the 3 pi plus 1. Okay, according to Green's theorem, which of the following line integrals is not equal to the area of the region enclosed by a simple curve C? So we know that Green's theorem states that the integral over C of f dot dr is the same thing as, oh sorry, I should be more specific. The integral over C of p dx plus q dy is the same thing as the double integral over the area R of q dx minus p dy dA. And so we can use this fact to answer these questions over here, because essentially what we'll be looking for is for when we apply Green's theorem to these guys, we want these integrands to work out, these integrands multiplied by the coefficient out here to work out to 1. Because if we end up with the double integral of r of 1 dA, well, that's just the same thing as the area of the region times 1. So let's figure this out. In this case, p is negative y and q is x, and so this integral is going to become 1/2 times the integral over r of x dx, which is just going to be 1, minus p dy, which is going to be another 1 dA. And we see that this will work out to 1 dA. And so answer choice A is not right. And we can move on from that and see that answer choice B and C are just individual halves of our first equation. We have an x dy, negative y dx, negative y dx. And these will, you can work through these on your own. This by the same method we use for answer choice 1, because they have a coefficient of 1 out here, will work out to the double integral over r of 1 dA. Okay, moving down to answer choice D, we have 1/3. Well, we should know what P and Q are first. So P is y, Q is 4x, and so Q dx is going to be 4, minus P dy is going to be minus 1, and so our integram becomes 3. We divide that by 3, and we get the integral over r of 1 dA. So that's perfect. But it also means that answer choice D is wrong. So let's see what happens with answer choice E. P is 4y, Q is negative x, and so Q dx is negative 1, minus P dy is negative 4, so we have the double integral over r of 1/5 and negative 5 dA, and this will work out to the double integral over r of negative 1 dA. And that is, I'm told at least, that negative 1 is not 1. So E is correct. Okay, let's find the gradient of the divergence of f dotted with the curl of f. Gotta love these questions that make you do bunch of operations. Not really. So we're given f here, and let's just start from the inside. We know that the divergence of f is del dot f. There we go. And we can do that. So the del operator is going to be partial x, partial y, partial z, and we are dotting that with f, which is xy, yz, zx. And going through all the motions on this, we will get y plus z plus x. Perfect. Okay, what's our gradient of this going to be? Well, that's just going to be, we know how to take a gradient, that's just going to be 1, 1, 1. So there's our first half, and now we just have to dot this with the curl of f. The curl of f, we know that's del cross f, so we can set that up. Partial x, partial y, partial z, and then we need f on the bottom. X, y, z, x, z. And there we go. So we are ready to solve everything. Okay, so this cross product is going to give us negative y, comma, negative z, comma, negative x. And so we are dotting this with negative y, negative z, negative x, but thankfully we are given some points to work with. So we are going to get negative y minus z minus x when we actually do our dot product, except x is 1, so negative 1, z is 2, so minus 2, and y is 1, so minus 1. And wait a sec. I think I'm confusing myself here. Let's see. Negative y minus z minus x. I'll actually go in. I went in reverse order in that last time and confused myself. So negative y is going to be 1. Negative x is going to be negative 2, and negative z is going to be negative 2, and negative x is going to be negative 1. This all works out to negative 2. It's interesting how the the addition at the end, at least for me right now after doing, I think I'm on my like 4th hour of recording today. That's what really fries my brain instead of the actual calculus that comes before it. I don't know. So here we go. Question 16. This is looking like a pretty good candidate for Green's theorem. We can rewrite it in the terms that we normally see it. See how they put dy dx? We can write this as the integral of c of negative 2y dx plus x plus y cubed e to the y. Oh, this is supposed to be a y. Oh no. Y cubed e to the y dy. And we can assign our p and q. Our p is just going to be this thing, negative 2y, and our q is going to be x plus y cubed e to the y. And so we know by Green's theorem that the line integral over c of p dx plus q dy is the same thing as the double integral over the region bounded by the path that we're taking of the partial derivative of p with respect to, no, this is wrong. The partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. Yeah, and if you're watching this in order, I just realizing now that when I wrote Green's theorem earlier, I wrote it as q dx minus p dy dA, which is not exactly untrue, but it's also kind of misleading. This is more accurate. And if anyone brings that up, I think I'll have to go and redo it. But it's a little secret for now. So let's figure this out. We need, let's see, setting up our double integral, we need the partial derivative of q with respect to x. Well, that's just going to be 1. And then we need to subtract the partial derivative of p with respect to y. That's just going to be negative 2. And so we are going to get an integrand of 3 dA. So now let's take a look at the region that we are dealing with here. We're looking at a trapezoid with the corners 0, 0, 4, 0, 2, 1, and 2, 3. So I've drawn it pretty small here, but if we zoom in, we can split this guy up into regions that will be easier to evaluate. This is 0, 0, 0, 4, 2, 1, and 2, 3. So just by doing some like simple area calculations, this little thing has an area of 1, this has an area of 1, and this has an area of 4. So the total area of this thing is 6, and since we only have a constant in here, we can just say that this double integral of r with respect to a multiplied by 3 is just going to be 18. But careful, we're not done. There's a magic word in the question. We're going clockwise around the trapezoid. And if we're going clockwise as opposed to counterclockwise, we need to flip the sign. So whatever we get in the end, flip it, and we're done. Let's find the surface area of the surface with these parametric equations. So we know that this is going to be expressed as the double integral of r times the, sorry, there's something on the tip of my pencil. I thought it was broken. Times the magnitude of RU cross RV dA. And that's it. So let's find RU and RV. RU is just going to be the partial derivative of R with respect to U, and we will get 1, 1, 0, whereas RV is going to give us 1, negative 1, 2. And we can take this cross product and we'll be good. So let's see. Our first cross is going to give us 2. Our second cross is going to give us negative 2. And our third cross is going to give us negative 2. And so we can take the magnitude of this. This is going to be the magnitude of 4 plus 4 plus 4, so root 12. And the integral of root 12 du dv on 0 to 1 and 0 to 1 is just going to give us root 12. And we're done. If s is the part of the paraboloid z equals x squared plus y squared with z greater than or equal to 4, and n is the downward positioning normal vector. This is important, the word downward. That's going to influence things later on down the line. And f is this, then we are looking for this integral right here, f dot n ds. So we know that we can find this whole thing by taking our f, which is just x, y, z, and dotting it with our normal vector. And in this case, our normal vector is going to be made up of negative zx, negative zy, and 1. But careful, that's the classic one. That's the classic setup, except we're looking for the downward positioning pointing normal vector. And as you can see, our z term here is positive, so it is very much not downward pointing. We can flip all these signs though, and it will be. So let's find this. X, y, z dotted with 2x, 2y, and 1. Whoops, sorry, I meant negative 1. That took me a very long time to figure out. I went through the entire problem, had no idea what happened, and it's just because I dropped a negative 1 there, which is kind of scary. So let's work this out. This is going to be 2x squared plus 2y squared minus z, where we know that z is x squared plus y squared. So this is just going to be minus x squared minus y squared. So our integrand is going to work out to x squared plus y squared ds. And we know that we can take this integral and turn it into the integral of the xy plane projection of our surface. And since looking at what our graph tells us, we see that our surface is expanding out to be if we look at this top path, it is a circle of radius 2. So all we have to do is integrate over the polar form of the circle of radius 2. So this is going to turn into the double integral from 0 to 2 pi, and from 0 to 2 of, well, this is going to be r squared, and then we have another r, so r cubed dr d theta is going to be r to the fourth over 4 on 0 to 2, which is 4 multiplied by 2 pi, and we get 8 pi, and that's our answer. Let's evaluate the integral of the curl of f ds using Stokes' theorem. It's a generally good idea when Stokes' theorem comes up if they tell you to evaluate the line integral of cf dot dr. Almost all the time, really what they want you to use is the double integral over s of curl f ds dot ds. And so these two are really interchangeable, and if you see one, they're usually trying to get you to use the other one. So let's see, I think this one case might be the outlier though, but I do remember saying that in the Stokes theorem video when I did this question before. It might have been this question, it might not have been, and I was wrong. So let's see. We have f, which is negative y, x, y, z, which looks like it kind of looks like a pain to take the curl of, that's for sure. And yeah, in fact, f dot dr looks like it's going to be easier because, so we're dealing with the sphere here that lies above the xy planes. So we know that for Stokes' theorem, all we need to do is to parametrize a curve that encloses what we want to integrate over. So we know that we have this kind of hemisphere coming up here because we're looking at the part of the sphere of radius 2 that lies above the xy planes. So this guy is cut by x and y roughly. So you can kind of see how we're dealing with a hemisphere here. So the parametrization of this boundary down here at the bottom can just be x is 2 cosine t, y is 2 sine t, and z is 0. And that works out very nicely because when we plug in r into f, this whole component with this big xyz is just going to vanish into thin air. So let's form everything up and do something that we can deal with. So r of t is going to be 2 cosine t, 2 sine t, 0. R prime of t is going to be negative 2 sine t, 2 cosine t, 0. And f of r of t is going to be negative 2 sine t, 2 cosine t, 0. So f dot dr is the same thing as the integral over c of f of r of t dotted with r prime of t dt. And so we can work this out. This is going to be the integral from 0 to 2 pi, because we need to go all the way around our hemisphere, of 4 sine squared t plus 4 cosine squared t plus 0 dt. This will work out to 4 dt, or just 8 pi. And finally, yeah, I was just looking for those magic words. We are oriented upward which is what we did. We went around counterclockwise, and so 8 pi is our answer, as opposed to negative 8 pi if we were oriented downwards. Okay, let's do this last question and get out of here. I'm starting to get a headache. Okay, we're using the divergence theorem to evaluate the double integral of f ds, where s is the boundary of the solid. A lot of the time, some of the time, they will not tell you to use the divergence theorem, and you'll have to realize that it's a divergence theorem, one, by the fact that it's either question 19 or 20, or by the fact that they say like a solid region or a bounded region or the solid boundary. They said that once, I think in 2019 spring. So, it's just doing it enough so that you get used to what magic words you're looking for. But in this case, we see our magic word is solid, so the divergence theorem is good to go. We know that the divergence theorem states that this guy right here is going to be the same thing as the volume integral over, they like to call it E. Oh, look, they do call it E, of some region E of the divergence of f dv. And we can find that. So the divergence of f is going to be del dot f, and all we're really doing there is taking the partial derivatives of this guy, this guy, this guy with respect to whatever component they are, and adding them together. If the steps that I'm skipping in here are ones that you think you should catch up on, feel free to go. I made a whole video doing all the divergence theorem questions, and they're eventually, hopefully in a couple of days, probably definitely by the time you see this, the majority of you, there will be a video for every single subtopic for the entire syllabus. So, anything you don't remember, go check that kind of thing out. So divergence of f in this case is going to be, don't want to write it there, divergence of f is going to be y squared plus z squared plus x squared, which works out very nicely because now our triple integral is going to turn into a rho squared dv. And since we're already putting that in spherical coordinates, it's very nice that really what they're looking for is the volume of the sphere of radius 2 in the first octant, where x is greater than 0, y and z are all greater than 0. So we can replace these things with another rho squared sine phi d rho d phi d, not another phi, d theta, where theta runs between 0 and pi over 2, phi runs between 0 and pi over 2, and rho runs between 0 and 2. So doing this, rho to the 5th over 5 on 0 to 2, that's going to give us 32 fifths. So now our integral has become, if we realize that we're not dependent on theta at all, our integral can become pi over 2 times the integral from 0 to pi over 2 of 32 fifths sine phi d phi, which is going to be, well, let's move this out here. That might be easier. 32 pi over 10. This is going to be negative cosine of phi on 0 to pi over 2. This is going to give us 1 times 32 pi over 10, which is 16 pi over 5. And we're done. Thank God. Okay, thanks for, if you made it all the way through, thank you for putting up with all that. I hope I cut it enough to make it bearable.